Now, we have, again, the product of two functions we want to rewrite in a way that's simpler to compute, so we're going to use integration by parts again. But in this case, the function we're transforming does not get simpler when you differentiate it. It gets simpler when you integrate it, because it already is a derivative. So we'll let dv equal x prime. And v is simply x. So we can get back the solution if we treat the derivative as our dv. And that means that the exponential this time will be u. And then du is negative s e to the negative st dt. So reducing it by integration by parts, we first have the product of u times v, which is e to the negative st times x of t from t equals 0 to infinity, minus the integral from 0 to infinity of v du, or negative s e to the negative st times x of t dt. And just like when we transform t, we're going to look for patterns in the limit comparing our function in the exponential, and then look for patterns in the integral to write it as a transformation of something we already have. So we take the limit as t goes to infinity. Here we have x of infinity, which we don't quite know, and e to the negative infinity, which we do know. So let me write this as x of t over e to the positive st on the bottom. And then we plug in 0, and we get minus e to the 0 is 1, x to the 0, x of 0 is simply an initial condition. And then look at this integral, and we have an e to the negative st times an x. That looks like the product with the function x. And negative s is just a constant, so we'll bring that constant out. And we get the transformation of x. So let's first think about the limit. By L'Hopital's rule, the limit of this infinity or infinity case can resolve to a finite value as long as the derivative, the ratio of derivatives, resolves to a finite value, or further and further and further derivatives. Now the exponential will just keep out spitting s and s squared and s cubed, and it just stays an exponential. The x, we're really not quite sure about it. X prime, x double prime, triple prime so far. But what's required is that x itself needs to be exponentially bounded. That's one of the requirements for using the Laplace transform. As long as x is exponentially bounded, which means that it grows no faster than an exponential. It can grow as fast as an exponential, but no faster than an exponential. Then this ratio will eventually reduce down to a constant. And that constant, assuming we can choose a large enough value of s to knock out any other exponential on top, will reduce down to a 0. So we saw that example with t. We've seen that example with cosines, sines, and exponentials. We can reduce it down. This is a major assumption in the kinds of functions that we can transform, or the kinds of solutions that we can use this Laplace transform method for. Here, the transformation can be rewritten as either L of x or shorthand, capital X of S. And another way to write this is that the transformation of a derivative is S times the transformation of the function minus the initial condition. So differentiation transforms to multiplication, which is exactly how the characteristic equation works. We turn every derivative into the eigenvalue, or R value, times what's left over. So we'll see the characteristic equation popping up when we're solving differential equations. And what's also interesting is the initial condition itself gets sucked in to the algebraic equation that we'll be solving. So the Laplace transform not only transforms the equation, but it transforms the initial conditions into the equation. So here we have a sneak peek of the next section, 6.2, where we're solving a differential equation with just first one derivative, first order equation. Now this happens to be a linear differential equation, so we can check our answer by using the integration factor method, but I want to show you how Laplace transform works with it. So first, that's not enough room right there. So first what we do is we transform the left and the right hand sides, and because of linearity I can write that as the transformation of x prime minus the transformation of x equals 2 times the transformation of t. Okay, and let's look at the pieces we have. The transformation of x prime turns into s times the transformation of x. It's a capital X. And then minus the initial condition, which is 3. We'll plug it in, but I'll leave it out there in this form just a minute. Minus the transformation of x, that's just a capital X of s. And on the right, the transformation of t is simply 2 over s squared. Okay, now to solve this algebraic equation for capital X, what we'll do is write it as s minus 1 times capital X equal to a 2 over s squared plus that 3 from the initial condition. And here we have the characteristic equation. X prime minus x turns into an s minus 3, or previously we saw it as r minus 1. S minus 1, or previously an r minus 1. So this is the characteristic equation back from chapter 3. Not the matrix form of the characteristic equation, although that is the same, can be used in the same form, but the exponential form of the characteristic equation. And so capital X can be solved for as 2 over s squared times s minus 1 plus 3 over s minus 1. Now, I'm going to leave it in this form because the problem didn't ask me to solve for little x. It just asked me to transform the differential equation, and I happen to solve for capital X just to make it as simple as possible. The goal from 6.2 is to then invert this by matching patterns. In our table, we have a 3 over s minus 1. That looks like an exponential. So I have 3 times e to the t. It's kind of cool. And then something else that we need to work a little bit harder on. This will require us to use something to break it up into a sum of fractions. And that something is called partial fraction decomposition.